Now we're live. All right, so we're going to talk about geometric sequences and something called series. And I'm going to do a flashback to last time and talk about the sequence 3, 5, 7, 9. This one is arithmetic, right? Because it has a
Common difference.
common difference. And the common difference here is
Those two.
2. That's easy enough. Where D here equals 2. Okay, so what's the difference then between the series on the left and the sequence on the left and the sequence on the right? We're multiplying by 2. Pardon? Common multipling, that's what you might think.
Common product.
But they call it a common ratio. Now, ratio implies fraction, and of course, common ratio is going to be called R for ratio. And how do we figure out what R is? Well, you take the second term and divide it by the first term. So 6 divided by 3 is 2. And then we have to check out whether it's equal to the third term, which is 12, divided by the second term, does it?
Yeah.
Yes. And then we have 24 over 12, and they all equal 2. So that is the common ratio. Yes.
How many would you need to test?
You have to test them all, because if there's one that's not,
You got
there it is not what we call geometric. So a geometric sequence has a common ratio instead of a common difference. Okay, so let's recall the formula for the nth term of an arithmetic. You remember what that was,
A
Josh?
It was A1,
A sub 1, yep.
is plus n minus 1 times d.
Perfect. And the things that we had to have filled out were A sub 1 and D to make it specific to a sequence. Well, that's great. That's for arithmetic. Now let's find the general formula for the nth term of a geometric sequence. I'm using my finger because I noticed online, when you listen to it, you can hear me tapping on the board. And so I'm trying to, be a little quieter about it maybe, I don't know, we'll see. All right, so knowing this, if I have A sub 1, well, that's just equal to the first term. I guess nothing to do with that. So how do I get to A sub 2? I take A sub 1 and do what to it? Multiply it by R, yep. And then if I want to get to A sub 3, what do? We take A sub 2.
2R.
Well, not 2R.
R squared.
Right, but I'm going to say A sub 1 times R, even though we all know that's R squared. Just to see if we can see the pattern. And then A sub 4 will be A sub 1 times R times R times R. Yep.
Can I say what I'm thinking?
Are you thinking A sub n? Are you ready to go there?
Yeah,
All right, go.
I think it's A sub 1 times R, and R is to the n minus 1 power.
Yes, nice. Good. What? Yep. And so this is the general formula. For the nth term of a geometric. Now, similarly to the general formula for the nth term of an arithmetic, we have to have a sub 1 filled in, and then we have to have r filled in. Nice. Well, we're so happy you can tell us that. All right, so let's figure out, using the sequence we have above, which was 3, 6, 12, 24, ... Let's find the nth term for that sequence. Yep.
So 3 times 2 to the n minus 1.
2 to the n minus 1, nice. Now, I like to harken back to Taylor Swift, and we are never ever, these two are not getting back together, right? Because they are not the same base, are they? You cannot multiply these together. Never ever multiply these together unless they're the same base. Yeah.
Seems like a familiar function.
It is exponential, isn't it? Now, what's really cool about this is that this formula, you can see a sub 1 and you can see r staring at you, which is really nice. This is an explicit definition. And what do I mean by explicit?
It explicitly states what they are.
Yep. It's explicitly defined. If I tell you what n is, I can tell you what number, you can tell me what number you're at, or you know what the number is in that position, right? Well, you can also define this recursively. Oh, what do I mean by recursive?
So would it be the number before it times?
Yes. So the recursive definition, that's a U, I can't spell, but you all know that. Which depends on the term before it. So if I wanted to go to the a sub n term, I'd have to know the term before it, which would be a sub n
Minus 1.
minus 1. Well, what do I have to do to the term before it to get to this term?
Multiply by 2.
Multiply by, yes, 2, but maybe I
Oh,
call it r. And then for our formula, you're right, it would be a sub n equals a sub n minus 1 times 2. That would be the recursive definition for, this formula. I was just, kind of doing the general recursive there. Okay?
I don't get recursive.
Recursively defined means,
Why is there a substitute for a minus 1?
okay, because, let's say I wanted to know a sub 4. A sub 4? That means n is 4, right? I want a sub 4, that means I have to take a sub 4 minus 1, which is a sub 3, and do what to it? Multiply by 2. That's a good question. The hang up for this is, let's say I wanted a sub 1000. If it's recursively defined, what do I have to know? A sub 999. And if that's not readily handy, then we have some trouble, right? So it's best to, I think, use explicitly defined, or that's probably the one we'll use the most. Okay? But if you see it out there, that's what that means. All right, so let's play the game. Is this geometric? All right, 3, -1, -4. Is that sequence geometric? No, and how do you know? You could say -1/3 is certainly not equal to -4 over -1, right? Right? No common ratio there. So we can say that this is not geometric. It's not even arithmetic, is it?
No.
No, because the difference here would be 4 and the difference here is 3. Yeah, so it's not even arithmetic, it's, so those are numbers. And they are related.
But we'll get up.
What happened here? This is, you said 3? No, it's 4, right? I'm sorry, and this is 3.
So it's
Or -1, -6, right?
So it's adding one less each time. So
Yes,
we're
but so we can
subtracting-
figure out the pattern, can't we? And then the common difference here would be 1. So this means, these are finite differences, we call them. That means that it's gonna take a quadratic in order to work it out. Okay,
I remember.
but I'm not ready to go there. We're just babies in the sequence and series world right now, so let's just, there is a pattern, but we can't see it right away, okay? All right, what about this next one?
Yep.
It's geometry, yes.
Geometric for sure. And what is R?
2.
2.
It's 2. Good, now if I wanted to write its general term, or general formula for the nth term, it would be a sub 1, which is
-2.
-2 times
2 to the n minus 1.
2 to the
-1.
n minus 1. Now, oh my goodness, that certainly looks like they might be the same base. Except, you know, if I can leave the negative out, and what happens when you multiply things with the same base? What do you do with your exponents? You add the exponents together, you're right? So this would really be -2 to the n. Now,
What?
I don't recommend that you do that because what happens? Do you see what a sub 1 is anymore?
No.
And you don't see r. So I am perfectly okay with you leaving it like this. Okay. Moving right on, is the next one geometric?
No,
No, not geometric.
Guess if you want to. Next thing.
Yeah, but you know, Mr. Boss, you're right. You can see the pattern and you know what's happening, right? I mean, the next term's gonna be what? 1/5 and then 1/6. So could we actually write an nth term for that?
Or you put 1 over in the arithmetic function.
1, yeah, you can do 1 over the arithmetic. Or could you just say 1 over, if this is n equals 1, this is n equals 2, this is n equals 3. What are we doing to the n? Well, we are increasing it. If this is n, what am I doing to get to 2? You're adding 1. So this would be 1 over n plus 1. And yes, you could use the arithmetic formula if you weren't sure. Because is that an arithmetic sequence on the bottom? Yes, you can do that, yeah.
Would it simplify back?
Yeah, it would simplify to that, yeah. Sure would. But it's not arithmetic itself, right? Because 1/3 minus 1/2 is certainly not equal to 1/4 minus 1/3, right? So it's not arithmetic either. But it doesn't mean we can't spot the pattern. All right, what about this next one? 4/9, -2/3, 1.
It's garbage.
It's garbage. So this is how we're gonna figure it out. We're gonna say, okay, I'm gonna have to do some math. I'm gonna say -2/3, I'm gonna take the second term and divide it by the first term, which means I'm gonna keep change, flip, some magic, math magic. And so this would be 9/4, which gives you
-1.
-3/2, good. And then I'm gonna check out the next one, which is 1 over -2/3, which is equal to -3/2. So what's R here? So this is geometric in disguise. So what's the moral of that story?
Don't assume.
Always
Don't
judge.
assume, and you should just divide them to figure out if the R's existing, the R common, are the same. Okay, so A sub n here, the generic, general formula is gonna be, well, what is a sub 1? 4/9 times negative 2/3 to the n minus 1.
2/3 or 3 half? It's
Oh, no, yeah, I'm looking at the second term, you're absolutely right, sorry. Thank you for keeping me honest. You're absolutely correct. Nice, okay. What about this next one, yep?
Is it in arithmetic standard?
Well, if I wanted, the common difference here would be what? 3?
3,
They're all
5.
zero.
and then the difference would be
Oh, yeah, it's like 1 squared, 2 squared, 3 squared.
Yes, you see the pattern, but then, right, and what, could you predict the next number?
16.
16, I like it, and then
25.
25, so what's the difference here?
7
7,
and 9.
9,
And the difference between.
and the difference between these is 2, so this is a quadratic in nature. If the common difference is in the first finite difference row, then it's linear, which would be our a sub n equals a sub 1, would be arithmetic in nature, right? This would be arithmetic. I can't spell. This was gonna be quadratic. Now what happens if I have to go one more?
Cubic?
It'll be cubic, but I'm not gonna make you do that, so
Wonderful.
do you remember this? 8th grade. That's pretty cool, that you were there, that's 8th grade. So this is clearly not what here though? Not geometric, nor is it arithmetic, but could we come up already, Renee said, this is nothing but a sub n equals n squared. Because what is n here? N equals 1,
I get it.
n equals 2, n equals 3. And sometimes when I don't know what the pattern is, I'll put the n's up here, and it will help me figure out what we're doing. And then if I have time, maybe I will show you how to solve this so that you can, this is a really cool thing to be able to solve. But not today. Because we are in our infancy.
Vulnerable.
We're vulnerable, yes. And I don't want you to be overwhelmed. One step at a time.
Oh,
One
Uh,
step at a time. Okay. Write a formula for the nth term of the geometric sequence.
Got it.
So they're telling you it's geometric, so we know that it's gonna be a sub n equals a sub 1 r to the n minus 1. I'm gonna say that so many times today that you probably have it memorized, right? That's the whole point. So do we know a sub 1?
2.
There's 2. So this is gonna be a sub n equals 2 times,
-4.
-4.
good, -4 to the n minus 1. Now you don't have to prove to me what r is if you see it. Everybody got that? Now, let's say I wanted to find like a sub 50, what would you do? You would just put in a sub 50 equals 2 times -4 to the 49th, and you put that on your calculator and get a very large number.
-6.34 times 10 to the 29.
What is it?
-6.34 times 10 to the 29.
Woo! That's big.
Lovely.
So what does this physically represent here, this a sub 50? This means this is the 50th term in
Switch.
that sequence. It's huge. It's growing exponentially,
Whoa.
right? Is this an exponential function?
You can't have a negative in parentheses.
Sure you can.
Well, but n has to be an integer and positive.
Yes, because by our very definition, n is by, remember, what is the domain of these things? N is an element of the positive integers.
You only get prime if you try to do like my fraction. Or like, I mean, a fraction.
It's growing exponential, integer, how do I say it, exponentially?
I just thought like when we were doing,
Well, I know, when you have an exponential function,
you can't put a negative.
you can't have a negative base, but in this case, are these sequences continuous?
Yeah. Oh.
No, because there's a whole bunch of numbers between here and here, right? I mean, if I let n equal 1, n equal 2, because this is my domain, the counting numbers. So are there a bunch of numbers in between? Yes. And our domain is just 1, 2, 3, 4, so we can have a negative base there, can't we? This was a great discussion to have. But the numbers are growing positively and negatively, yes.
So, but it won't form an X because it will up and
Right, exactly, yeah. You're getting let me put it this way. The absolute value of the numbers are growing exponentially. Is that better? It's getting infinitely large and infinitely small, right? Because negatives get small. Okay, that's mind blowing. We're just gonna move on. Okay, here we go. Bigger the other way, okay. But the number's smaller. Right, because numbers get bigger this way. Get smaller this way.
But,
Yeah, so, anyway. Discussion for another day. Write a formula for the nth term of the geometric sequence given as the first term in the common ratio. Not everyone at once?
A
Negative
sub
one.
n
A sub n equals
negative
negative, and I'm just putting a negative on the outside.
6 and minus.
Oh, that was tough. Next one. I know.
Is this gonna be the test?
3 times negative
Would that be nice?
n minus 1.
I know. He's singing too.
Oh, I like the next one too.
I'm rubbing off on you, boy.
Oh, a sub 2.
Uh-oh.
How nice is that?
Nice.
Boom, next. But things in life aren't always that simple.
Sadly.
Never, right? So let's find a formula for the nth term for the geometric sequence given a term that's not the first one in the common ratio. Yep.
So you could replace a sub n with 18 in this case.
Yes, yes. So he's saying that they're giving us an n, aren't they? They're saying n is 2, and a sub 2 is equal to what? A sub 1, which we don't know, times negative 1/9 to the first, because it's 2 minus 1.
Wait a second. If you multiply the a sub 1 by 1/9, wouldn't it be a 9 or whatever it was?
Yeah, but that would be this term.
No, if you multiply by 9, you get a sub 1, right?
Yeah, that's what we're gonna do.
That's what we're gonna do.
That doesn't show that.
I'm just showing this algebraically. Oh no, something interesting is gonna happen. What's gonna happen for solve for a sub 1?
Oh,
Yes, sir.
This ends up being the recursive.
Yes. It does end up becoming the recursive. So what goes here now?
Negative.
162?
So then.
Magically, I knew that. Maybe because of. Okay, so what happens here when I multiply? I want to just do the third one just for kicks.
let's go with 2.
-2.
Negative 2. So this one is an alternating sequence. I love the corner that you were intuitively knowing what to do without setting up algebraically. That's great.
Should I do alpha 3?
Be nice if you could, but I mean, I do like the fact that you were able to do that, okay? But that's not too bad either, is it? But things in life aren't really that easy ever.
Oh, this one was fun.
I'm not really a fan.
Okay, so let's say I'm gonna give you two terms, but not R, and one of them is not a sub 1. Yep.
So the difference between them is n, so it has to like
There's four
Yeah.
and six.
product.
So this is a sentence for each other. Ours are, be like, A5, both with negative 64, and that's the negative 1000, like, over A5, just.
Yeah, I like that possibility. What if it was a sub 12? Would that work?
Yeah.
So in this case, that would work. But I'm gonna give you a way to do this where it works every time. Would you like to know how to do that?
Why not?
Yes? All right, so what are they telling us here? They're giving us two n's. So n equals 4. So we know that a sub 4 is gonna equal a sub 1, which I don't know, times r, which I don't know, raised to the third. But a sub 4 is negative 64 equals a sub 1 r to the third. All right, what's the other thing they're telling us? N equals 6.
A sub 6.
A sub 6 equals a sub 1, which I don't know, r, which I don't know, raised to the fifth. And then I can say negative 1024 equals a sub 1 r to the fifth. Yep.
Since you know that they're not zero, can we divide them?
Yes, you can. And I want to have a discussion first before we do that. Is r ever going to be 0? Okay, so let's pretend for a second r could be 0.
The sequence.
What kind of sequence would that be? You might have term number 1. No, you wouldn't even have term number 1.
I mean, wouldn't also be arithmetic.
Yeah, I guess it would with the difference of 0, right?
Couldn't you have term number one?
You could have zero.
Yeah, you could.
Term number
one could be.
Could be 5.
Yeah.
Right.
Wait, Miss Moore.
And then it would be 0, 0, 0, right? Has that pretty boring sequence? Yes.
So that would be arithmetic and geometric.
Well, I don't know. We're not gonna go there. But
Whoa.
could r be possibly 0 in this case where I'm getting two different numbers here? The answer is no. Right? I mean, if r was 0, these would be 0. Okay? So, the other thing I want to point out is these are two equations, right? This is a system. But it's not a linear system, is it?
Sadly.
No. It's an exponential system. And you can't solve exponential systems with linear combination. You can use substitution, but I like Anna's idea, which was to divide them. Because what happens if I set up a ratio, and I always put the one that has the highest exponent on top? So what happens if I say a sub 1 is to a sub 1 r to the fifth, is to a sub 1 r to the third, which is kind of a version of what you were doing, equals,
Negative 1024 over negative 64.
negative 64. Because if you divide them, what happens to a sub 1 every time? It cancels out. Beautifully cancels out. All right, so then we get on this side right here, r squared equals
16.
16. So r here could be
Plus or minus 4.
plus or minus 4.
And we can't tell because we only have a sub 4 and a sub 6.
So we have two possible sequences.
I don't know how you got to divide.
I'm just suggesting that you could do that. You could set up a ratio,
Oh,
a ratio.
I see it.
All right, now. So if r equals positive 4, what is a sub 1? We gotta figure that out. And it doesn't matter which equation you use, but let's use the easier one, shall we? Which is the one that's raised to the third. So we can say negative 64 equals a sub 1 times 4 to the third. Negative 64 equals a sub 1 times 64. So a sub 1 is negative 1, right? So what would our a sub n be for this sequence? It would be a sub n equals negative times 4 to the
And -1.
n minus 1. That's my first sequence. This is the first possibility. Let's check out the second possibility. That's going to be with r equals negative 4. So we have to figure out what a sub n would, a sub 1 would be for that sequence. So I'm going to say negative 64 equals a sub 1, which I don't know, times negative 4 to the third. So this is negative 64 equals a sub 1 times negative 64. So a sub 1 here in this sequence is 1. So that means our a sub n here would be 1 times, you don't have to show the 1,
4 to the n.
negative 4 to the n minus 1. So let's see what happens here. 1, 2, whoops. 2, 3, 4, 5, 6, And they told us that the fourth term was what, negative 64, and the sixth term was negative 1024, right? So for this sequence up here, what happens? We said a sub 1 was negative 1, and if I take negative 1 and multiply it by 4, we get negative 4 times 4 is
-16.
negative 16 times 4 is,
-64.
it works, right? Times 4 is negative 256, so it works, because we were given this one and this one, and it fits right in, doesn't it? What?
Like 2048, the game. It's all the numbers.
I know!
Yeah.
How cool is that? Yes.
Anxiety.
When we did the one with the negative r, we cubed it, so it kept the negative.
Yeah.
But what would happen if we had to keep extra? Would you lose a solution somehow?
No, what happens is, if you have one, if it's even, no, it works out every time. Because what happens is you're gonna always have two cases. If you have, what happens if you divide them and you get an even exponent, you will have two possible sequences. Okay? Like if you had r to the fourth or r to the sixth, you know, depending upon what the two equations are. And you would just use your r as the positive and r as the negative, and it would give you two different.
So we'll give you the same base one.
No, I have to think about it, Anna. Can I think about it? I'm not ready to go there. Shall we see if this one works?
Yeah.
I'm sorry, you guys are so quick that sometimes you think about things while we're going, and I can't keep up with you, which is a good thing. 1, 2, 3, 4, this is negative 64, and this is negative 1024, so let's see if this one works. A sub 1 here is 1, and then times negative 4, times negative 4, 16, negative 4, negative 4. Okay, so this one is alternating, but it still fills the bill, doesn't it? So that's nice. I don't wonder where they got that expression. Is that like?
It's really cool.
Falcon fill or something?
No, it's because they're trying to fill up the bill with a bunch of words, so like, you know, like a passing bill. They're trying to fill with words so you don't understand.
Is that true?
I don't understand.
On the east of the A push you can.
Alright,
Oh, no.
we're using technology.
All right, so I know that you can do this now, it's pretty simple. I gave you the hardest case possible, which is where you'll have two possible. All right, so I'd like to go on, if that's all right? Now, let's pull the calculator out and see if we can have some fun. So we're gonna change our calculators to sequence mode. Okay?
Whoa.
Okay, now, what is a sequence? It's a collection of objects in a certain order, right? Our sequences are a list of numbers. So I think we're gonna press second list. Okay, you guys with the 89s are gonna go, math, yeah, second math, and then, go to your list menu, and it's gonna be the first one. You see it?
How do you do it on the?
You're gonna go second math, and you're gonna go to the list menu, and it's the very first one. You have to stay with me.
I'm just ready for drawing.
And I appreciate it, but you know what? Did you find it? Second math, list, and then you got the sequence, which is the very first one. Okay, all right. So if you have an 84, do you notice that this comes up? Does it come up for everybody? Except for,
Yeah, but I'm using your calculator.
okay, yes? All right, so then what you do is you go sequence, and then you don't type your nth term expression. So let's do the one that we just did. Okay, and let's use the, nth term for the first one here, is that all right? Where we go negative, and I would use parentheses, 4 to the, and you raise to the exponent. Now, you guys hang on for the 89, okay? All right, so you type in your nth term expression, everybody got that? And then you're gonna type in n, because you gotta tell the calculator what the variable is. And then where are we gonna start? Position 1?
Is N represented?
We're gonna start with position 1. All right, and then let's end somewhere. Where would you like to end? 7, okay, you type 7. And then,
Talking about start as in like the end number,
no, it's the position you're starting in.
like end, the end.
Yes, so I always start at 1 and go to 7. Unless I'm trying to find the 1,000th term, and then I go from 1,000 to 1,000. Okay, everybody got that? So I can now talk to the 89 folks? On the 89. What you're gonna do is this popped up, didn't it? All right, and so now you're gonna type your equation, which is negative 4 caret raised to the, now, yep,
Do you want the negative inside the, or?
no, I thought it was outside, right?
It was outside.
And then if you wanna use n, you can use n, so that you have to go alpha n, and the alpha n is above the 6. No, and, whoops, I'm sorry, because then it would be n minus 1, comma, and then you have to tell the calculator what the variable is. What is the variable? N, comma, and where do you start? At position 1 and end at position 7. So that's the 89.
And there you go.
Everybody see it? Let's see, did you get your sequence? You just press enter, 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 go. And one more time.
Yeah.
Here it is, and now remember,
There's
you
two-
don't hop up to arrow over, you arrow over where you're sitting. You guys can on yours,
Is the n minus 1?
okay?
Oh.
You see it?
Mhm.
Yes, sir.
There's supposed to be 2 of them. Oh, but this is one.
I just did one of them, okay? Did you get it, Kevin? Brian, did you hear it? Everybody follow? Yes, ma'am.
I didn't get rid of the word.
Okay, let me get over there.
Yes. Yeah. No sequence.
Okay, so second quit. All right, so you're gonna go second list, ops, sequence, there we go, you got that. Oh, you gotta tell the variable to be n, because n is a variable, okay? Enter, 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 and then now one more, there it is. Now, to see the rest of the terms, you have to arrow over. from where you're standing. You don't hop up, you just arrow over, okay? Everybody got
Yeah.
it? Nice. Okay, so just for practice, let's do the other one. How did we get there?
Second, what?
Second list,
Ops.
ops, number 5. How did we get there on the 89? We went second, math, list, and it's sequence, the very first one. Okay, and so it's gonna be the same here on the 89. It's gonna have parentheses -4 to the n minus 1, comma, n, comma, 1, comma, 7.
Where's
All right?
They don't get the whole template thing.
No, I think the 84 pages you a bit.
Here's more.
Wait, next year, can we have both?
You can, but I think you're gonna find out you like the 89 better, don't you think so far?
Yes.
And I don't make money off of selling 89, believe me, but you have to take alpha and alpha and,
Okay.
I like how mine cuts off. Because
okay? Everybody's capable of doing that now? That's pretty simple, and you have the instructions now in your notes. So on the 89, let's just refresh your memory, how did we get there? We went second. Math. List. Sequence, right? These are kind of like, just for your own memory, okay? How exciting is that?
pretty sweet.
All right, now,
It's like the calculus.
here we go. Now, what amazing things, when you have a list of numbers, can mathematicians think about doing to all those numbers? We got a list of numbers.
Sigma.
We could add them all up. Of course, they're there, we should add them,
That makes sense to me.
right?
They keep going.
So, sequences can have a long list of numbers, can't they? All right, so someone invented this thing called summation notation, and when you add a sum of a sequence, that's by very definition called a series. So a series is nothing but a sum of a sequence of numbers. All right, now, summation notation here is a shortcut way to write a long list of numbers that you're adding together, okay? So let's talk about this, and I'm sorry that this is cut off, but this is k equals 1, and this is 2 here. Now, what this is a Greek letter S, and I'm never going to ask you this, I'm just going to tell you the Greek letter S for sum. That's why they named it, you know, the Greek letter S, sigma for sum. It's sigma. And the lower, below the sigma is what we call the index of summation, which is k. And the lower limit of summation is 1. That means we're starting at position 1, and then the upper limit of summation is 6 here, and that means we're going to add from position 1 to position 6 together. Okay? And so this is shortcut notation for what another way I affectionately call this k equals 1, the counter. You know, the counter, and we're going to start counting with k equal 1. So we're going to plug 1 in here and we get 1. Boom. And since this is a sigma, meaning sum, we're going to sum. So it's going to be a plus. And then I bump the counter up to 2, and then this is 4. Good. And then I bump the counter up to 3, and we get 7. Bump the counter up to 5 and we get 10.
4.
Okay, oh, 1, 2, 3, 4, you're right, I'm sorry, I'm ahead of myself. 4,
Good.
we get 10. We bump the counter up to 5, we get 13. Bump the counter up to 6, and that's 16. So this is a sequence that I am adding up. This is a series.
It's like math.
It is. So this is shortcut for writing all of this out. Now you're looking like, well, maybe it doesn't look like quite a shortcut, does it? Because I had to sit there and write the terms out. But your calculator will do this without you writing them out. But I wanted to show you how to write them out. So this is equal to 51, by the way.
Just good.
Okay? So we're summing a sequence, aren't we? On the 84, now there are going to be 2 sets of instructions. So you guys with the 89s, close your ears for a second. You are going to go to the math menu on the 84. So you're going to go math, and then you're going to go in the very first column and scroll down until you see something called summation.
Oh, whoa.
Whoa.
Everybody got it?
Awesome.
Yes? And then what happens when you hit the summation?
Yeah.
You get
That's great.
a lot of little boxes.
Let me see.
I didn't.
Scroll down. We have to update your software. Did you get it? Summation, what pops up? A lot of boxes. You got a box here, you got an equals, you got a box here, you got a box here, and you got a box here. Is that correct?
Yeah.
So what do you suppose is gonna go here?
Okay.
Okay.
Okay, but we don't have, yes, we're in sequence mode, so it'll be N. If you are not in sequence mode, you can use X.
And it'll still work.
It'll still work. But let's put N here, right? Equals what?
1,
1, and then you hop up here and you put a
6.
6. And then you type your expression here, 3n minus 2. All right. And then you press enter and it gives you the answer. Ladies and gentlemen with the 89s, you're going to go home, or you're on the home screen. You're going to hit the F3 button up top. You see it? Oh, did something pop up? Okay, there it is. All right, now, sadly, it doesn't make me very much. What happens is this opens on the 89, and then what are you going to do? You're going to type in, and you can use X if you want, 3x minus 2, comma, you tell it the variable, which is X, and then where are we starting?
1.
1, and we're stopping at 6. It was so fast, wasn't it? Everybody got it? Now, how do you know if you're right on the 89? You get that nice pretty print once you, so you can see whether you're right. Isn't that nice? Did it work? You see how you'll be able to tell if you're right. So did you all get 51? That's nice. All right, so let's do this next one. And this is I equals 2.
Whoa. Oh.
I like to do this, get it? I like to do this with a different variable because it doesn't matter if it's K, if it's I, if it's X. Okay? So let's expand this one first. So what happens when I let the counter start at 2? We get the square root of 4, which is
2.
2. Okay, you guys are moving slow. Okay, 3 root 6.
Oh, I know words.
Okay, sorry. 4.
2 root 2.
Good. 2 root 2. 5. Root 10. It's okay. They don't have to be pretty. 6.
keep thinking it's a square root of
Just give
negative.
me a second.
Oh, don't go there, don't go there, that's why I did it, to get you over that. All right, where was I? So this is 2, 3, 4, 5, 6, what's 7? Root 14 plus 8. 4. Woohoo! Right, 2 times 8 is 16. I don't want you to be intimidated.
There's a great number that comes out in the calculator.
What about 9? 3 or 2. Okay? Now, when you put that in the calculator, what do you get?
25.8889.
Now, the 89, I think will give it to you exact.
Yeah,
Yeah.
it just gave me a long list.
What is it?
It's a long list, but then I approximate it.
Oh, yeah, you don't want to do that.
I want to decide.
Yeah,
I don't want to match it.
yeah, right. You don't want the imaginary guy.
If you put the I for the thing, it's imaginary.
Actually, I have my switch because it's parameters.
Let me see. Did it work with the, yeah, he just did it with X. I wouldn't use, yeah. Here it goes. Yeah, he used I, and he's all right. He used the letter I versus. All right, we okay? All right, well, I'm gonna let you guys, this should have one more parenthesis, by the way. So I'm starting at 1 here. What happens when I let I equal 1? We get 1 minus 2, which is -1. What if I wanted to see what the sequence was? Without having to. No, yeah, without having to think, yeah. Yeah, how do I do that? Second list, go. Second list. Now where you see I, you can put N. Right? So the end of the third minus parentheses N plus 1. So somebody's gonna give you the sequence, right? And we're going from 1 to 5.
-1,
Okay, hold on. -1 plus what?
5,
Plus what?
5,
5 plus
23,
23 plus
59,
59
119.
plus 119. All right, and that equals 205? 205. Nice. Somebody asked me last block, Mrs. Mother, what if it's a minus here? If the next number is a minus? Well, so what are you doing? You're adding a negative, right? So it'd be -1 plus -4. So yeah, you are subtracting, but you're really adding a negative number, so that's okay. All right, questions on summation notation? No? None? It's really easy. It's kind of algorithmic, isn't it? Can you back to the computer frames? Find the sum of the arithmetic sequence, or arithmetic series. Why do we call it a series? Because it's a sum of a sequence. Now this is 1 to 17.
It's a calculator.
You can do
Yeah,
that in your
let's
head,
go,
right?
oh, yeah, okay. So what happens? Somebody do this on a calculator, let me know what you get.
This is error.
289.
Somebody says 289, concurrence?
Yep.
What about this next one?
Nine, 9, 4, 5.
So 9,900.
So you can do these on the calculator pretty handily, right?
And I'd probably
Right.
cry.
And you take a long time to do it.
Yeah.
You write like 12.
Wait.
What if I asked you to sit here and add up all the numbers from 1 to 100? Yeah. No, we're not gonna do that yet. Just go with me so I can develop my story.
I like this.
All right, will you?
I'll stay
It's
silent.
okay that you know the end.
The first
It's the journey that matters.
It's the journey that matters, right? And they haven't had the journey
Oh, I
that
know.
you had.
I thought you guys went over it
Oh
last
yeah, the
time.
math journey.
The math journey, that's right.
No, it's not.
And everybody's in a different place in their math
I know
journey.
this.
So let's get us all in the same spot, okay?
I have no.
If I were to ask you to add up all the numbers from 1 to 100. Here we go on the calculator. 1 plus 1, 2, right? What happens? By the time you get to 51, have you messed up somewhere sometime?
Probably.
Right? Well, there was a math student a long time ago named Gauss. He's a famous guy.
It wasn't me. They looked at me.
Anyway, and he was really irritating his teacher. And so the teacher said, I've had enough. You go to the corner over there and you add up all the numbers from 1 to 100. He thought that would keep him busy for a while.
Is this a true story?
Yes. Yes.
When did this happen?
When I was told it was a true story. So I believe it's a true story. So you believe it's a true story, right? Well, the teacher thought, well, he'll be busy for a while. But guess what? Gauss came back in less than 30 seconds with the correct answer. No, this was so long ago, they didn't have calculators. And the teacher goes, no way. No way you did it. And Gauss said, yeah, it's so easy. Challenge me. Come on. And so what happened here? We have the numbers 1, 2, 3, 4, 5, ... What? 96, 97, 98, 99, 100. And Gauss said, well, this really isn't that hard if you think about it, because all I did was I saw a pattern. I said, well, 1 plus 100 is what? 101. 2 plus 99 is what? 101.
What the heck?
3 plus 98 is 101. Oh my goodness! Challenge me. This is ridiculous. How many pairs of 101 do I have? 50. So all I had to do was say the sum is of 100 numbers was 50 pairs of 101. And I can do that in my head. That's just 50-50. Or 5,050.
That's a smart kid.
Very smart kid.
How old was he?
I don't know the answer to that. But they named Gaussian elimination after him. That's how bright he was. Clearly. Okay? So he saw a pattern when adding an arithmetic list of numbers. What did he do? Yeah,
What if it's odd?
does it matter?
But then you can't pair it.
It'll always work out.
So let's find out what the general formula for an arithmetic sequence is. It's going to be, if I had n numbers, what did he do? He put them in pairs, which means he took the total number of numbers, and what did he do?
5 by 2.
He divided them by 2, and then he took the first one and the last one and added them together. So he said, I'm going to take a sub 1 plus a sub n and add them together. Right, where this is the first term, and this is the last term. And he added them together. Yep.
So this only works if you know, like, if it has like a definite end.
If it has a definite end, yes, because arithmetic sequences go on forever. Don't that mean you keep adding 2 or, subtracting 6 or whatever, right? So this is the formula for the sum of n terms, I can't spell terms, of an arithmetic, and I'm going to underline arithmetic sequence. Arithmetic series, I should say. I'm sorry, arithmetic series. This right here. Yep.
So if you didn't have a definite end, would you just make n like
Yeah, you could, but let's think about it. Arithmetic sequences and series, arithmetic series go on forever. They're either always increasing or they're always decreasing, depending on how d is positive or d is negative. So you cannot add them up. All right, infinite one. So let's see if this works using this. What would my first term be? I would just let n equal 1. So when I put in n equal 1 up here, what do we get for our first term? Well, I'm going to say a sub 1 here. Let's do that. A sub 1 is equal to 1. A sub 17 is equal to, because that's the last one, isn't it?
33.
33?
Yeah.
So how many terms do we have?
17.
The number of terms is always, I'm going to call this, is always, this is n equal a to b. It's going to be b minus a minus b minus a plus 1. That's going to be the number of terms that you have in a sequence. B minus a plus 1 in a series. How many terms you have? So b minus a plus 1. So this is going to be 17 minus 1 plus 1. So we're going to have 17 terms. So the sum of 17 terms will be 17 over 2. This is exactly what you wanted. You wanted an odd list, didn't you? I must have known. Times, what's a sub 1? 1 plus a sub 17? 33. So this is going to be 17 over 2 times 34. So this is 17 times 17, which is 289. I just did it without a calculator.
Oh, man.
Thank you, Gauss.
There you go.
Yes.
So you said that's the formula for the sum of arithmetic?
Arithmetic, yep.
Arithmetic. Is there one for geometry?
You know I'm going there.
Was there another guy?
Well, I'm just trying to figure it out.
His name was His name was George.
George. Yes, there is. Absolutely is. All right, so let's find the sum of this geometric series.
Small here.
I'm gonna do this first one, is that all right? What's a sub 1 here? This is right, this is a sub 1 r to the, can I pretend? This is a sub 1 r to the n minus 1. You see a sub 1? Right, okay. All right, but, all right, so let's do this on the calculator. You give me a very large number. Because this is 1 plus 2 plus 4 plus 8 plus 16 plus 32, right? Because this is 2 to the 0, 2 to the first, second, third, fourth, fifth, sixth, seventh. Oops, that's 128. 256.
That's the 9. Yeah.
Right? So this is term 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 terms there, right? So what do you get when I add those all up? 511? Okay. Now there is no real nice story for this one, but I'm gonna prove it to you, all right? And so I'm gonna insert a blank page. So let's say we're gonna add up a sum of geometric. So it would be, the first one would be a sub 1 times, it would just be a sub 1 times r to the 0, wouldn't it? Yes? Yes? Plus, what's the next one gonna be? A sub 1 times r to the first?
Can you back that, but it's one?
No, but was I born knowing how to prove this to you? The answer is no. I saw somebody do it once, and then I knew how to do it. So I'm just adding them all up. So then this would be a sub 1 r to the second plus plus the very last one's going to be a sub 1 r to the n minus 1, right? Because I'm doing n terms. Now I'm going to create a second equation, and I wasn't born knowing that, but I'm going to do a second equation where I multiply all of those by r, both sides. So I'm going to say this is r times s of n equals, now I'm going to multiply r times everything else here, okay? But what happens when I do that? I get a sub 1 r, right? But I'm going to line it up with this one. I'm just going to have a space here. It doesn't matter where I write it, but I'm lining them all up. So just go with me here. This is a sub 1. A sub 1 r to the third plus plus a sub 1
To the RN.
r to the, well, I've multiplied, yes. Well, no, it's going to be r to the n, isn't it? Because I multiplied it by r. So what do? We add the exponents, and it's r to the first. Right? But what is the term in front of this one? If I were going to insert a term here, it would be a sub 1 r to the n, right? Plus a sub 1 r to the n minus 1, right? I'm just showing you what the term before the last one is. That's all I'm doing. Yeah.
Why do you subtract those ones?
Well, because that's the main, that's what my formula is for a geometric sequence. Or for sequence, it's a sub n equals a sub 1 r to the n minus 1. So their last one is going to have n minus 1. So this would be n minus 2. Would that make you happier? Okay. All right. Some wise person decided what I'm going to do now is I'm going to subtract these two equations. Now, was I born knowing that? It's gross, but it's going to turn out to be really nice. What happens is I get s of n minus r s of n equals, well, what happens to all of these terms in here? They all cancel. And this is going to cancel, right? And then this one is going to cancel, and then what's left is this last one. Everything cancels except for the first one and the last one. So we're going to have a sub 1 plus a sub 1 r to the n.
Oh, and then you just factor up the s, so that.
I'm gonna factor out the S of n over here, yes? And I get 1 minus r equals a sub 1, factor that out. 1,
Oh, wow.
but I'm subtracting, so this has to be a negative, I'm sorry. I forget about subtracting. Minus 1 minus, I'm sorry, r to the n. And so S of n is equal to a sub 1 over 1 minus r to the n all over 1 minus r. So this is, by definition, or by our proof here, the sum of a finite geometric series. Okay, so let's see if it works. It won't? It doesn't, I'm gonna have to cry. But I just proved it to you.
We'll never have to prove that, right?
No, you won't. I just been showing you. It's not too bad. I botched it a little bit there in the beginning. So there's my formula, right? I'll fix the box. For you OCN folks in the crowd. That's not perfect, but there it is. So how many terms does this sequence have, this series have? I'm sorry, it goes from 1 to 10. Oh, wait. What happened?
That's we didn't use that
That's a
one.
different one.
You know what
That's
happened?
the next one.
You know what happened?
You can just
What
write.
happened? You know
You
what
can just write
happened?
the old one's right there. That's
Like
what the old one
shifting
was.
Ah,
Just it was.
What's going on?
that's what happened.
Ooh.
Because it's not lock and play. Lock. And if I lock it, then things don't work nicely. All right, so what are we gonna do? And how many terms do I have? 9 minus 1 plus 1, which is 9. So we want S sub 9. Using my formula, this is gonna be a sub 1. Well, what is a sub 1? It's the one in the first spot, which is 1. That's nice. Minus, or times 1 minus r. Well, what is r?
The difference. Oh, it's 2. It's 2.
It's 2. You see it? 2 to the
9.
to the 9th, very nice, because we're using this formula. All over 1 minus 2. So this turns out to be 1 minus 2 to the 9th. 1 minus 2 to the 9th. It's 512.
511.
It's 512 though, right? And that's negative 1 on the bottom, which makes it 511. It works.
Wait a second. Why is the difference 2 for the R? Okay, sure, okay, I see. Never mind.
Okay? So what happens if there are infinitely many terms in a geometric sequence?
It's okay.
Would you just make an approach infinity?
Yeah, what happens if we let n approach infinity? The limit as n goes to infinity of s sub n. The limit as n goes to infinity of a sub 1, 1 minus r to the n over 1 minus r.
Does it approach infinity?
Okay, in our case where we had r of 2, what happens? This number is going to get bigger and bigger and bigger and bigger and bigger, isn't it? What happens if r is something like 1/2?
Then it put
It's smaller and smaller and smaller.
What happens when I raise 1/2 to the 10th? You don't need to calculate it quick.
It's like a tiny couple.
1 over
1/2 to
9.7. 8 times 10 to the negative fourth.
Negative fourth. What if I raise 1/2 to the 50th?
Really small.
Keep going, I wanna see it. What is the number?
8.88 times 10 to the negative 60.
Negative 60?
Negative
What?
16.
16. Let's do it, 1/2 to the 100.
7.89 times 10 to the negative 31st.
Negative 31st. How many zeros are in front of that?
Oh, 30.
30,
Whoa.
right?
It's being exact.
Wow, so what happens?
It gets
It's
so
closer to
small.
zero.
It is going closer and closer to zero.
If you put the 400,
Like-
it's a 0.
Yeah, it's the same.
The
Just a zero.
where it has the,
It's too small to register.
the asymptotes.
Yeah, okay, so what's happening if R is a special number and I use 1/2, what other number could I use 1 for?
Yes. Anything between 0 and 1. Right?
What about negative 1/2?
Oh.
Try it.
It's good to go like,
Negative 1/2, that has to be in parentheses, right, when you're raising it?
Only put it to 0 to the other side.
Yes, ma'am. It comes to 0 from the other side, doesn't it? I have positive going to 0, and then I have the negative coming. Yes. So what happens is absolute value of R is less than 1. That means R has to lie between -1 and 1. I'm telling you that I can add up an infinite number of numbers if R lies between -1 and 9. That's a little crazy, isn't it?
Okay, if R is absolute value of R is less than 1.
Is that sinking in? So what happens then? If R is, absolute value of R is less than 1, what happens to this term? You guys all just witnessed it, we just did it, what happens to it? It goes to 0, whether it's positive or negative. And so what is this limit? Equal. The sum of an infinite number of numbers is gonna be a sub 1 over one minus R. If R is that special number that lies between 1 and -1.
wait, why can't it be above 1?
So what happens? What's the number above 1 or -1? We just did it, 2. Okay, let's do 1.1 to the 100. Do it.
A big number.
Oh, it gets just huge.
It
instead of
gets
going to
enormous.
0.
Well, fractions that lie between -1 and 1 are special numbers because if you square them, cube them, you know, they get smaller and smaller and smaller, don't they? It's like taking a string and cutting it in half, and cutting it in half, and cutting it in half, and cutting it in half. And then I say, does that equal all those pieces? Does that equal the length of the string? Could I keep cutting whatever I have in half until the physics of my fat fingers and my, the scissors, the width of the scissors? Yeah, you could keep doing that, right? But if you kept cutting something in half and half and half and half and half, you still have the string, okay? Just let's see that paradox, getting closer to the door. Go halfway, halfway, halfway. You ever reach the door?
No.
But sadly, the physics of your body mass, right? There are other things to consider, right? So let's see if we can add up the one that is, has an R that is less than 1. Have your calculator do this and tell me if it gives you a number.
It's
And I'll see if I can go faster.
That's a stretch.
6 point.
Yeah,
6.39999.
is that equal to my 32/5?
Yeah.
How do you put that in the calculator?
Summation, you go to math,
Yeah.
summation,
Oh, that
and you fill in the boxes, right? So did my formula work?
Yep.
I was pretty fast. I had an infinite number of numbers. Yes,
So it's nice that we got 6.3999 and you got 6.4 because it's not credited.
did you get the 32 when you did that?
I got 6.4.
You were zoned down, how about you now? Did you get the approximate or did you get the 35th?
I got a huge number and then my approximate, which got me 6.
You can put your calculator in, exact mode, and it'll give you 32.5. Yeah. Questions on that?
I didn't have to go into it.
8.
How do you get to infinity?
It's the alpha.
I'm sorry. I was doing to infinity. So let's do your summation to infinity. How do you get to infinity? Guess what? There's an infinity key on here above catalog.
Wait, where is it? When you get the 32.
I'm sorry, we only did 10 terms. That's not helpful, is it? So what do you do on an 84 when you have an infinity on top?
Create a giant number.
There we go.
You went 1 to 10, right? Did you get a number? What'd you get? Okay. If you do a math graph, does it give you closing fractions?
Where's the infinity?
We'll talk more about it later. What's that? We'll make it at 10:30.
He normally is.
All right, start on my day. What?
How do I update it?
You have to come down to school and give me your calculators.
I'm bringing it tomorrow, like after my exam for that. I'm leaving.
Oh, yeah.
Thank you.
You're welcome. Have a great day.
Oh god, it was only 3 days ago.